Play here. Okay. Let me test this. Okay, so the title is not the one that was announced by the chairman, because somehow my poster and the talk got mixed. So about creep, I was talking at the poster, and here I will talk about strong pinning regimes explored with Ginzburg-Landau simulations. I would like at the beginning to thank the organizers of this wonderful workshop for inviting me to present our recent results that were obtained at the Argonne National Laboratory together with Alex Koshelev, who is here, and Ivan Sadovskyy, who is here, and Andreas Glatz. Okay. So this is a theorist's picture of a superconductor. It's gray and shiny. And if we apply a magnetic field and want to see how this superconductor looks like from inside, we open it and we see that there are vortices. And these vortices arrange in a hexagonal lattice. And the not so nice thing about these vortices is that when you apply a current, then these vortices start moving. Their motion is associated with dissipation, and this is what we don't like, because we like the resistive free state of superconductors in order to have them in some applications. So what can we do about this is we can just throw defects into the superconductor, and these defects will prevent vortex motion and therefore restore the dissipation-free transport of electrical current. This dissipation-free regime is only realized if the current is below a critical value, and this critical value is the critical current, and it is about this critical current that this talk will be centered. So here is an outline of my talk. I'm going to explain you how we can, as theorists, think of critical current, how we can describe them. For this, I need to revisit some ingredients, and then to see what are the predictions. And I will focus on strong pinning theory. We had already 2 talks this morning about this, so I will be rather brief on this. Then we have at Argonne a large-scale Ginzburg-Landau simulator, which allows us to simulate actually a pretty large volume. And then we are going to look if we can identify regimes or parameter range where this strong pinning theory applies. And once we have found these regimes, we also know where the simple strong pinning theory does not apply. And this will allow us to find how can we correct for this once we are above, beyond the regime of applicability of strong pinning theory. And then as a last topic, I will talk about a new phenomenon that we observe for large inclusions, which we call peak effect, because we see actually a very non-monotonic behavior of the critical current, especially for large inclusions. So what are the ingredients that we need for describing, let's say, critical current within a strong pinning framework? What we need is, first of all, defects. And these defects are characterized by different things. On one hand, we have the size of the defect, which more or less gives us how strong the defect will act on vortices. And we have here numerical values for how the size of the defect, these are metallic defects in our case, how they result in different pinning forces. Then we have the density. Gianni mentioned in his talk that strong pinning theory assumes low density of defects. So we will see how this depends on density. And then just one single vortex line will have a line energy. And in the case of an anisotropic superconductor, you need to account for the anisotropy. Now, if we go to finite fields, then there is also vortex-vortex interaction. And then we capture this usually in some effective elastic constant, which is roughly given by the line energy divided by the intervortex distance. Now, once we have all these ingredients together, we can see what are the results, what are the predictions for the critical current. And we identify 3 regimes of strong pinning theory. One regime we call the 1D strong pinning regime, where essentially the vortex is isolated from all the other vortices and has to optimize its line tension versus the number of pins that are visited. And in that case, one expects the critical current to scale like the square root of the number of particles or the density. and to be independent of the magnetic field. And these scalings are highlighted here. So square root NP dependence and no dependence on the magnetic field. Then we have the classic 3D strong pinning regime where we have this elasticity appearing, we have the transverse scattering length appearing, and then the critical current is expected to scale linearly with the number of defects and to have a dependence which is a bit more complicated than 1 over square root b. Usually this elastic constant is expected to scale like 1 over square root b, which is the dominant field contribution. But then there is this T perp, which also has some field dependence, and this gives, usually in the case of potentials which decay like 1 over r squared at large distances, we expect the critical current to decay like this power b to the minus 5 over 8. And then there is a high field limit where actually all the defects are occupied, and then in the naive picture one says, well, the pinning landscape can provide a maximal pinning force, and pinning force is equal to current times field, so we expect that that the critical current should decay like 1 over the magnetic field. And also in the dilute case, and in the case of dilute defects, it should also be proportional to the defect density. Now we are going to look at these scalings and how they work in simulations. So let me spend a few words explaining what we do in the simulations. As I said, we take a big volume, usually 100 times 100 times 50 xi. We put in this volume a certain number of defects. In our case, they are metallic defects, and this defines as a density. Then we fix the magnetic field. This more or less tells us how many vortices we have in this system. And we apply a certain current, and at each current value, we monitor the voltage. And then we decrease the current and monitor the voltage again as we decrease the current, and then we see that we go through this dynamic to static transition. And because it's not just linear and then 0, we take a criterion of 2% of flux flow voltage as a criterion for the critical current. Now here for 250 defects and a field of 3% of HC2, we find one value of the critical current, but we can repeat this for many more defect numbers and many more fields. And then we have a JC map, which is here in a triple logarithmic scale. So we increase the field by 2 orders of magnitude, we change the density by 2 orders of magnitude, and then we have this nice map. Now, in order to explore these scalings with the density and with the magnetic field, we will take projections of this 3D map. And the first projection I'm going to show you is the projection, which is the projection through this window. And then we see that if we look at the lowest field, which is this set of points in the back, that they agree very well with the scaling that we expect in the 1D strong pinning regime, which is the scaling with square root of the number of particles or the density. If we go to very high fields, then we also see that we have a nice agreement with a linear scaling with the defect density. And at intermediate fields, well, we see that the low density regime is well described by linear scaling, but then we have a deviation. Again, this is in a log-log plot. So these straight lines here are parallel because they are linear in density, and this is flatter because we have square root density. And we have so we see that we have a slight disagreement here at high densities, and how we want to attack this problem to correct this this behavior at high densities is that we have observed that in the 3D strong pinning description, one can associate healing volume to vortex, which is deformed by defect. And this healing volume more or less tells us on which volume does the vortex return back to its undeformed, unperturbed form. And if we go to higher densities, then there is a probability to find more than one defect within the same healing volume. And this will then lead to a competition between two defects for the same vortex. And one can calculate what this competition will produce. And what we find is that it corrects the critical current, which we know from the 3D theory, by a correction which is proportional to the density and proportional to the healing volume. And there is a numerical factor in the simple model that we calculated, this factor is a bit smaller than 1. And here from the simulation, it suggests that this number is a bit larger than 1. In this case, I showed the data for nu equal to 3. And with this, we can account for this correction at larger densities. And we see that these corrections are like n squared, yeah, because we have a linear dependence at low densities, and then we have corrections np squared. Now let's look at the projections through the other window of this 3D critical current map. And this is showing here at very high densities the dependence of the critical current as a function of field, again in a log-log plot. And then we can do this for all the other fields, all the other densities that we have. And we see two things, and there is a third thing which we don't see. Let me start with the latter one. What we don't see is that the critical current saturates at lowest field. So we don't see a saturation, which tells us that we are not truly in the 1D limit, because we still have a field dependence. We expect that if we are at low enough fields, then vortices are so far apart that they don't feel each other, and the critical current should not depend on field. And this we don't observe. So for this, we need to push our simulations harder to go even further down in field. However, we see two things in the current view, is that there is a region where the critical current depends like a power law as a function of field. And then at very high fields, there is a kink, and then the critical current drops much faster. And actually, we can associate this transition from one regime to the other by the field at which all defects get occupied. And this is exactly the transition which we expect when we go from 3D strong pinning theory to the high field regime, where actually all defects get occupied. Now let's focus on the 3D regime and just plot the theoretical predictions. We see that for the lowest densities, we have a very nice agreement with the theoretical expectation, but quite rapidly we see that at higher densities, the theoretical prediction deviate from the simulations. But as I explained before, we know that we have corrections which we have to take into account because of density corrections of defects. And if I insert these corrections, then we see that for a much larger field and density range, we have a very nice agreement between the simulations and the theory. Now, if we go to the high field regime, and here again I show what we expect from theory, then we see that we have a very large discrepancy between what we expect from the theoretical considerations and what we see in the simulations. In particular, I would like to draw your attention on the fact that the slope, which is giving us the power at which the critical current decays as a function of field, is much steeper in the simulations than what we expect from theoretical considerations. And I want to spend now a bit of time focusing on this particular issue. And for this, we have simplified the problem even more. So what we now take is we take a volume, and this volume is shown here, and we just put one isolated defect in this volume, and then we perform simulation on this simple system. We have a ordered lattice, we have one defect, and we look what is the depinning force of this defect as a function of field. So here is a picture of the critical state, just when this defect, this vortex depins from the defect. But we can actually, from the simulations, even make a movie and see that the vortex depins at a certain current, and then the next vortex jumps in. And from making such movies, we can actually extract more than just the pinning force. We can also extract this length, which Gianni was introducing this morning, which is the length at which the subsequent vortex becomes unstable and jumps into the defect, and the length x plus at which the vortex is critical and then jumps out of the defect. And we can perform this, okay, and these are the values. We can perform this for higher fields. In our case, we chose to have a field-dependent system size in order to always have the same number of vortices, so we have always a lattice of 36 vortices. This is why the system size changes as a function of field. And in this case, we see that the second vortex becomes roughly unstable when the first vortex is departing, and this is also reflected in this x plus and x minus. So we find that at relatively high field, which is a third of hc2, x plus and x minus are about the same in size. Now, we have performed this for more fields, and what we can do is we can make a map of this x plus and x minus as a function of, here it's the intervortex distance, which means that here we are at low fields, and then we go to higher and higher fields. And we see that as we drag a vortex up along this vertical axis, at some point this vortex becomes unstable, it deepens, then we have a region where the defect is unoccupied, and then at a later stage the next vortex, which now here is rescaled by one lattice period, will jump into the defect, and then it will stay in the defect. And what we see is that for the highest field, the defect is permanently occupied, and therefore once one vortex decides to leave, the next one immediately jumps into the defect. And this is also reflected in the pinning force that we observe. So we see that the pinning force is actually a function of the magnetic field. So the naive expectation that we just have one pinning force characterizing the defect is not anymore true. We have to account for the effect of the next vortex, which is actually pushing behind and kicking out the first vortex. This reduces the pinning force, and this leads to a field-dependent pinning force. And if we, this is from the one defect simulation, if we scale it up again to this lowest density simulations of 125 defects, then we just multiply essentially the pinning force. We translate the pinning force of one defect to the effect of 125 defects, and then we see that it explains very nicely this this stronger decay than the 1/b dependence. Okay, now I come to the last topic, which is the peak effect for large inclusions. And actually it's similar to what I just showed you, only that now I change from relatively small defects of 2 psi diameter to larger particles. And this is actually data which Alex showed 2 years ago in El Escorial. And he actually showed the critical current for large particles, there are 500 of them, as a function of the magnetic field in a log-log plot. And below that critical current map was even the plot showing which fraction of the defects are occupied by 1 or more vortices, by 2 or more vortices, and so on. And you see that also here we have a kink, which is associated with the fact that all defects get permanently occupied. But this plateau, which was observed here, it took us quite some time to understand that it's actually associated to the fact that now every defect is occupied by 2 vortices. So the vortices are big enough to hold more than one vortex at a time. And this leads, in this case, to this plateau effect. If we push the simulations to even lower defect densities, we see that this plateau even gives room to a maximum in the critical current. And in order to investigate this maximum more closely, again, we take the simpler situation of just one defect, a large inclusion, and a nice vortex lattice, and we study the property of this one isolated defect. So here, again, are the pictures of the critical states. We see that as a function of increasing field, we have 2 very different pictures. Here in the critical state, we see that one vortex is sitting in the defect, and the vortex which is in the back, you already see that it's getting unstable because it starts to deform towards the defect. And the instability actually in the critical state is that of the second vortex becoming unstable and kicking out the first vortex. In this case, the critical state consists of 2 vortices sitting in the defect, and then the first vortex decides to leave the defect. And we can also look at the movies. We see that the vortex in the back becomes unstable, stays for a while with the first defect, and then the first defect leaves. Whereas in this case, we just have two vortices sitting, and then one decides to leave, and then a third one can enter. Here again, we can quantify this phenomena by evaluating x plus and x minus, and now we have a much more interesting phase diagram. What we see here in the top corner is similar to what we saw for the smaller defects. So we see that up here we have a regime where one vortex leaves a defect. For a short time, the defect is unoccupied, and then the next vortex enters. Here we have a quite large field range where when one vortex leaves, immediately the second vortex decides to enter the defect. And then at highest fields or smallest intervortex distances, we even have a regime where the second vortex decides to enter the defect before the first one leaves. So we have here a region of double occupancy of the defect. Now, another thing which is very interesting to observe is that within this region where we have double occupancy, there are two competing states. One is that of two vortices sitting in the defect, and one is that of one vortex sitting in the defects and the next vortex trying to push the first vortex out. And these two states have a different energy, so one can imagine that as a function of field, we transition from one being the minimal energy state to the other being the minimal energy state. And this we clearly observe by just looking at the movies and evaluating which one of the states is the critical state. But this is a first order transition, so we see a jump here. If I plot what is the state which is the critical state, then we see that we have a discontinuity in this quantity. But moreover, what we see is that in the force as a function of field dependence, this first order transition results in a kink of the force that you need to deepen a vortex from or the vortex system from the defect. And this is a very strong kink, which actually leads to almost a doubling of the pinning force as a function of field. So here you are at a fifth of epsilon 0, and here we are at 2/5 of epsilon 0. And this point where this kink appears is exactly the point where we have this first order transition. Now again, we have a field dependence of the pinning force, and if we translate it back into our critical current versus field diagram, we see that we have a very nice reproduction of this data. And the understanding that we now have is that this non-monotonicity, which we have here, is associated with the transition of two different minimal energy states. Now let me conclude. So we have investigated with simulations the three regimes of strong pinning, which is the 1D strong pinning regime, where we actually see a square root NP behavior, but we have not pushed our simulations hard enough yet to really find the field-independent critical current. The 3D strong pinning regime has been found, but quite soon, as a function of density, we leave the regime of 3D strong pinning theory. And I think we can very well account for this deviation by taking into account defect doublets, which correct the critical current. And at high fields, we have a linear dependence in the magnetic field, in the density, and the decay of the critical current, which is faster than 1/b, can be understood by the fact that the pinning force is not a field-independent quantity, but acquires a field dependence, because vortices which are in the back, they would like to enter the defect. And for large inclusions, we even see a non-monotonic behavior of the critical current. With this, I would like to thank the funding agencies. I would like to thank my collaborators on all. Well, I have a variety of projects which I'm involved in, and I would like to thank these collaborators, and I would like to thank you for your attention.